various and so on. So okay, so why do we want to have distributed systems, right? That's a fundamental question. Like, and if we go deeper down, there are two aspects. One is scalability. We want our systems to perform well, be able to handle high load, be able to handle high data, for example, in databases, be able to handle high transactions. If it comes to Amazon, if it comes to Google, be able to handle many clients across the globe. So that's the one thing. And second thing is we want these systems to be high available. Now, back in those days, nobody really thought about high availability as an aspect of distributed systems. But if you look at this picture, it's basically one log of wood that cannot be carried by a single person. That's what today's systems are. Put whatever amount of computing resources in one single server, it's not capable of handling the entire load end to end. And if one of the pair of hands goes down, right, the rest are going to fall apart. And that's where really the high availability comes into picture. And that's why high availability becomes an integral part of any distributed system. In fact, now these days, you will not see a system which only cares about scalability and does not care about high availability, or vice versa. Again, now look at high availability picture, and you will see that there are already two resources there, and one of them is active. I'll let you decide which one is active, okay? And the other is passive. So in such systems, initially, it was thought that this passive system is actually, we are wasting resources, keeping that passive system just there for availability's sake. And so the thought started, why not to start using that passive system? We have gone through a lot of changes in that travel. We started using those passive systems as hot standbys, where we could offload some of the work, but not all. And that degree started increasing. And now these days, both of these are actually active, as is required in the seesaw, by the way, that both of them need to be active. So that's really the aspects of high distributed systems that are required to be investigated, looked upon, and taken care of when we architect a distributed system. And these basically are the fundamentals of any system, any distributed system that we need to care about. When it comes to databases, these can be broken down into two sets of features. High availability, again, something which predates scalability in terms of distributed systems. The requirements are that the system should be up for 24/7. When it comes to databases, the data needs to be available 24/7. Now, remember the difference between data being available and system being available. These two are separate things. And that's true with every distributed system. We don't want our systems to be operating 24/7. We want the functionality to be available 24/7. Okay. And well, the second is this 24/7 is quantified as how many nines you attach to it. What's the time it takes for the high availability to be restored? How long a system is highly available? And the current requirement I see is 5 nines, but I'm sure it's going to go further beyond. The third is disaster recovery, where if something happens to, some disaster happens somewhere, you don't want to lose the functionality. Again, it's about functionality, not the system. Your system can blast. It can be blasted by a volcano, by anything. What we want is that functionality that the system provides has to remain and should be available. Kind of tied with 24/7. At the same time, it's also different. I mean, it requires a different thought process in order to be disaster available beyond disasters. Whereas the usual availability does not necessarily consider disaster in there. We'll come to that point. And a further progression to disaster recovery is actually being available anywhere. We want the functionality to be available anywhere, whether I'm in India, whether I'm in US, well, outside the earth now. We want that functionality to be available. We want that data to be available, right? So we can see the progression right here of high availability, how it has evolved over the years, and how the requirements are getting more and more stringent. Coming to scalability, well, at least in terms of databases, there are 3 V's that used to be considered as the scalability, the parameters of scalability: volume, how much data you can process, how much data you can store; velocity, at what rate we want that data to be handled, that data to be processed; variety, this is again something that has evolved a lot over these years. Long back, all that the database needed to handle and store was integer types, floats, strings, maybe emails, but now it's, I don't know what not. I mean, there is multimedia, and multimedia itself has so much variety in it that this aspect is also getting, I mean, it is important when we talk about scalability. And having all that variety of data to be processed, to be ingested, stored, it affects each other. So there is some performance angle. This also affects velocity and volume when it comes to building these systems which handle this variety of data. And now we want the scalability everywhere. We cannot say that just because I'm operating from India, my system will be slow, or I won't be able to ingest some data. Like if you see the way AWS instances have evolved, earlier there were just regions in US, Europe. Now we see regions in India, right? That's because we want the system to be scalable wherever I am, okay? So, and that adds the 4th V, I would say, in the list of scalabilities. Now we'll talk about, we'll switch more to the databases and especially Postgres, because that's a field I have been working for quite some time. So I will take that as a base and yet touch upon the general databases and distributed systems. For PostgreSQL, if we look at the bare PostgreSQL is still a monolith. It's still an SMP solution. And thanks to the improvements and advances in the machines, it's still catering to high workloads, being still SMP. But that's not enough, of course. What happens is, if we look at the community, the way community progresses, it accepts the feature, it takes time to accept these features which are complicated. So what the middle way is that PostgreSQL community or core PostgreSQL, what we call, exposes certain features that allow us to build systems, build distributed databases on top of PostgreSQL. So you take stock Postgres, add your features, and then it acts as a distributed system. There are three ways to do it. One, do it yourself. Take PostgreSQL, start using these features, and a bare minimum distributed system is available to you. And by the way, if you have listened to Zerodha talk in PGConf India this year, you will see that they have developed such a system on their own without any help from the commercial vendors. That's one thing. It's complex, but it's doable. Second is create extensions which can be plugged into PostgreSQL, just like you plug extensions into your Chrome or other browsers. You plug them in PostgreSQL server, and these extensions allow you to run a distributed system. The third is create a fork and build your system from scratch, like what Postgres-XC was, like what Yugabyte is doing. But all of these flavors of building the distributed systems are usually based on the 4 pillars, I would say. 2 kinds of replication, which allow high availability, partitioning plus FDW in some or other form, which allow distribution. They take care of the scalability aspect. And there is this glue of extension, which basically brings these 2 worlds together and gives you a distributed system, which is both highly available as well as scalable. Now, I'm still reminded a lesson that I learned probably 10 years back is, although I said that the distributed systems are built with 2 goals, high availability and scalability, these goals are competing. The moment you throw scalability, high availability gets hampered because, in order to be scalable, you need to throw resources, and those resources need to be highly available. The moment you improve high availability, your scalability is impacted because now those resources that you could throw into high scalability are now used for high availability. So, those are the 4 factors. And basically what I have done in this slide is I have kind of graded them based on a feature that they provide, based on the capability that they provide. For example, streaming replication, you won't get 5 nines there. You will get 24/7 availability, high availability, disaster recovery certainly, but you won't get 5 nines. Whereas logical replication actually takes care of or has potential to take care of all the high availability aspects right now. Whereas it also, in some cases, do scalability thing also. I mean, it can support some level of scalability. Whereas partitioning plus FDW cannot give anything in high availability, but it does a lot in the scalability arena, not so much in the everywhere, being scalable everywhere. And then it's the extensions, which by themselves will not give you much, but they, as I said, they are glue. So they are all yellows. But when you combine 1, 2, 3 together, basically you get a distributed, highly available and scalable system. So what I'm going to do is I'll talk about logical replication, partitioning, and extensions one after the other. The databases, if you go back to your books, database books, you will remember that the databases have 2 views. One is The physical view, which is how the disks are laid out. The second is the logical view. That is how the user see a database. The tables, objects, rows, columns, that's the logical view. The bits, bytes, pages, that's the physical view. Now, when it comes to physical replication, what it does, or streaming replication, what it does is it makes sure that if given multiple systems, one of the systems is primary and the other systems are secondary, and those other systems are exact physical replica of the primary system eventually. Which means that if you really look at the disk layout on the secondary systems, it looks same as primary. That's the physical replication. And exactly because of that, it cannot serve 5 nines, because it takes some time for the first system, the primary, to go down or get detected that it has gone down, and then the secondary to come up, be up to the speed with the primary, and then start giving functionality. That is solved by logical replication. Now, what logical replication does, it gives you the logical view of the database. It replicates the logical view of the database, again, with eventual consistency. Now, this eventual consistency is different from ACID, the consistency in ACID. Okay, that we have to keep in mind. So with logical replication, what happens is we can make changes to any of the nodes. These are, for example, here there are 3 PostgreSQL nodes. Make changes to any of those because all of them are serving as primaries, or they are capable of writing. And those changes are replicated to the other nodes. And that's how the logical view of the database is maintained. Of course, the physical view will be now completely different. And basically decoupling the physical and logical view allows us to do multi-master replication, what is called as multi-master or write-write replication. But the payment, the cost for that is you lose even consistency. The systems are not exactly consistent. It takes some time for the changes to travel from one node to the other node. That is one thing. The second thing is, if you change the data, same data on 2 different nodes, it creates conflicts. You might be changed, simple example of account balances. If you change same account balance on 2 different nodes, then those changes are going to conflict. Both of the account balances are wrong. So you need to consolidate those account balances. But with these hazards, if your applications are capable of handling these hazards, then these systems work 24/7, because 24/7 with 5 nines, because each system is now available. This goes down, you have 2 systems available for you to start writing. Even if this goes down, you have the 3rd system available for you to keep writing. And so ideally, logical replication has potential to extend those nines to any length, 5 nines, 7 nines, 8 nines, and so on. But theoretically. So that basically brings the very first aspect of distributed system. This evolution of replication builds one strong pillar of distributed system, because now the system is distributed and it's highly available. And we'll see how to make that scalable further. In fact, to some extent, this is scalable, because if these nodes are in different geographies, then the latency of the application is reduced. So in that sense, they are still something scalable. Any questions on logical replication? Yeah, I have to. So these are eventual consistent. So in terms of cap, we are losing consistency, whereas giving more more advantage to A and P. But at the end, we will see that Enterprise DB offers a solution where even C can be achieved at some cost of A and P. But you basically get a system where you can control how much C you want, how much A you want, and how much P you want. So you are not bound by, well, all for practical purposes, you are not bound by cap. You are not limited by cap. In theory, yes. There is no way that we can work around cap. Any questions on logical replication? I mean, I'm trying to explain things at a level where even the database novices or those who do not have database experience are able to understand. So, well, that the technology is established kind of thing, and everywhere, even in Oracle, PostgreSQL, it's called. I mean, there is a logical change that is sent. So, if we, let's say, update account balance on the first node, what gets transferred here is it basically sends a message to the other node saying that balance of account with ID equal to this has changed to this value. Or even in certain cases, I think from this value to this value, if we use certain data types, even the difference, the delta is transferred. So those are that kind of information is replicated rather than replicating the underlying blocks or anything. There was a question.
Okay, please use mic. Yeah, thank you. So am I audible?
Yeah.
Yeah. So the question is, you mentioned that this needs to be probably, 5 nines and also available everywhere in a way. Finance translates to about 5 minutes per year of downtime, which is kind of stringent and everywhere. So sometimes it's like people also tend to think of it in terms of like across geographies, right? So probably if one update happens in Europe, it is replicated in Asia. So how does that affect the performance of the system, given there is certain network latency or there are things which we cannot physically avoid? So if you could just share on that, that would be great.
Well, I'm going to add more to the geographic distribution. So I'll take this question.
We can
this is a good
look
question.
at it later.
Really good
Thank
question. As we will be propelled into the next decade of distributed system, these questions are going to be important. Yes, I'll take that at that time. Now, one aspect of distributed systems which I learned from this is whatever the distributed system is, whether it's your microservices-based distributed system or anything, the only solution to HA is redundancy. You have to throw in another redundant resource without which you cannot build distributed system. Any system which has SPOF, single point of failure, is not highly available in any sense because failures are not in our hands. What is in our hands is to add an extra resource and being able to switch to that extra resource, switch the functionality. That's why I emphasized in the beginning that we don't want high available systems. No, we want high available functionality. This system can go down, the functionality remains. Now, we can call that as a system in itself, this whole thing as a system in itself, but really the thinking when we are developing distributed systems, we should think about the functionality being highly available, functionality being highly scalable, rather than system being highly scalable, system being highly available. I mean, that's a takeaway, at least from this talk, if nothing else. The next aspect I'm going to talk about is foreign data wrapper. Slightly, I'm going to reverse the reverse the earlier sequence. So foreign data wrappers, and this is again ubiquitous. You will see this feature in almost all the databases in some or other form, in different names. But essentially, this allows a database to process external data, the data which is not in that server. And that is another aspect of systems today. Like back when, let's say, my grandfather processed his statistical data, he sent it to TIFR. There was this big room full of server where that got processed, and then this shipped a CD kind of thing to him with the processed data. That's no more allowed. We want the data can be anywhere. It could be in your S3s, it could be in your car, the sensor in your car, sensor in your house. It's everywhere, and still we should be able to, a database should be able, the system rather should be able to deal with that data. And that's where these kind of features come in, where they can process external data. So in a way, again, we are addressing the problem of variety. Variety of data, variety of sources of data. Not just data, also their sources. But as you will see here, there are already two elephants here, indicating two servers. So we have already thrown a distributed system, even when talking about foreign data wrappers. And this is one of the things that allows us to basically, when it comes to PostgreSQL, when it comes to database, this is the system which allows us to push the data to some external server, to some other server, process it there, and get the results back. Store it there. So it just, and that's where the first step of scaling is. You are able to use two servers in order to process your queries, store your data, and do whatnot with that data. The second aspect is partitioning. I mean, partitioning is now everywhere. It basically allows you to distribute your data. So you can distribute a large amount of data into smaller chunks. They are called partitions. They are called tablets in different forms. But that's what the partitioning is. And combine these two features. You have FDWs running here, and each server holds one partition of the data, one tablet of the data. Now you can use, for example, here you can use 4 servers in order to do the processing of one, in order to process one query by shipping the operations to those servers and consolidating the data from those. I think, so any questions on this aspect, the distribution, and maybe foreign data wrapper is something which all of you may not be familiar, but partitioning is something everybody is familiar. So any questions on this aspect?
Romit here. Okay, so I just wanted to understand, when you say that foreign data wrappers, are you like, do you mean that the different input sources we have in today's world, like Hadoop and S3 and all those things, or what does that exactly mean?
So it could be inputs, and it could be also output from the primary server, the source of foreign data wrapper. Both of those are possible.
Okay.
I mean, if you think about IoTs, a sensor linked via foreign data wrapper, that's an input. But if you think that you are using 2 PostgreSQL servers where there is transactions happening on one server, then the other server is, I mean, where you basically push the data also down. It no more acts just as input.
Okay. Thanks.
Okay. Now, let's combine all of those 3. And that's where you have a distributed systems, theoretically, distributed systems where you have sharding. as well as HA. So, I mean, I have given a very simplified diagram where there are 4 servers, they are connected by replication interconnect, and then the sharding interconnect. And these two protocols are slightly different. I mean, in PostgreSQL, we have combined them into a single protocol called libpq, but that may not be necessary for general distributed systems. Let these servers be distributed across the geography, and you get a geo-distributed system. Now that's possible for 2 reasons. One, logical replication, of course, sharding, but also the improvements in networking. They allow us to be able to deal with such systems. Now, coming back to the question, of course, there are latencies, right? An application sitting here in India, if it requires data from here, now the thing about a distributed system is the application will still talk to the server near to it, but that server might require to reach out to some other server in order to process the data, because that data would not be there with that server. In that case, it will hit the cost of latency. So there will be performance aspect which will be affected. Yet there are systems where even that latency is lesser than the processing time, the data processing time. So even in those systems, we have seen that it's a win-win situation. Of course, this is being built. This is not something, I mean, we have deployed logical replication across the globe, and we have seen it working. Of course, application needs to know where the data is so that it basically operates on the data nearest to it rather than running across the globe. But those systems are working. They are being used by well, I don't think I can tell the names, but banking systems, by the online shopping, online gaming, all those verticals, telecom, all those verticals, this system with logical replication is being used. I have seen it being used there. And with terabytes of data. So it's not even small amount of data that needs to be transferred. It's terabytes of data. Okay, any questions till now? I'm going to now slightly switch to a different architecture. I want to touch base upon that before we close this talk.
Hi. What I understood is the sharding helps you to distribute your data. So if your data is very big and it cannot reside in one single system or a server, you shard it, maybe using some key or any logic. So in this case, the application need to know, well, okay, I need, say, for example, this user data. So does application need to know to which DB I should hit? Or will it, or does application just hit a query, it will hit some database, and now database identify, okay, this data is not with me, I have to go to somewhere else and bring it there from there?
Okay, the answer I'm going to give you today is going to change tomorrow. But today, usually the systems are, the applications are more aware of their distribution. So you will see that their drivers or application logic take care of directing the queries to appropriate server. But we are building systems which will allow the servers to redirect those queries internally rather than letting application to do it. I mean, all this evolution, again, that this is another aspect of distributed systems. Usually, things have started from applications. Applications first started partitioning data at the application level. They started distributing data at application level. And then they started the system started absorbing it inside those. So right now, yes, applications need to be aware, but that won't be necessarily the case tomorrow. I mean, soon enough, that will change. That there will either we'll put that logic in the drivers or we'll put that logic in the servers to redirect the queries appropriately. Any other question?
Hi, this is Arkan. I have pasted a few questions in the channel. If you don't mind, can you have a look at them?
Hi, Arkan, can you just ask questions directly? We can hear you.
Okay. I'm only concerned that I may not be audible. Okay. So the first question that I have is, so even though we are having a kind of distributed database here, how good is that with eventual consistency? I mean, not many use cases, particularly with transactional workload in the OLTP kind of environment, may not be okay with eventual consistency. So is there some solution to achieve real-time consistency rather than just eventual consistency with this distributed setup? So that's the first question. Then the next question is,
Okay.
yeah, sorry, go ahead.
Sorry to interrupt you. The first question, I think I'll answer when I talk about the enterprise DB's offering.
Okay.
I'm not going to go into the details of that solution here because it's too complex, trying to control cap at that level, but I will touch upon it, the capabilities that we introduce.
Sure.
So just wait for that slide.
Sure. Yeah. So the second question is, suppose I would like to stream the changes, something like CDC. I want to do a replication of the changes, replicate the changes that are happening in the distributed database as such. I mean, the overall changes across different nodes, considering the multi-master setup and things like that. If I want to stream all of those changes, and which most of the companies have this kind of setup, right? They perform all of the analytics on different data warehouse environments and things like that. So in that kind of setup, if I want to stream all of the changes, we should have a global log of changes that are happening with the conflicts resolved. So for this, do you think there is a need for external transaction manager, which is actually doing the conflict resolution kind of thing, and then which would also have the actual changes in order, which could be streamed?
Okay, it's a quite good question, and it touches upon one of the problems that we have been trying to solve for quite some time, almost a decade. But I'll try to answer it nevertheless. Again, there are multiple aspects to it. One is capturing changes across the nodes. I think those can be captured in different ways. Either capture the changes on different nodes and consolidate them at the application level.
Yeah.
PostgreSQL allows you to do that using the logical replication protocol.
Right.
So you can, I think there are users who use Debezium to do it. What other option is to attach to a single node and accept all the changes. From it, basically in databases, no matter what, relational databases, the changes to a database is a single stream of wall records. So even if those changes are happening across multiple nodes, they are serialized on a single node. So even if you attach to a single node and capture the data, it is automatically serialized for you. You don't need to do further conflict resolution or serialization on top of that. That's other option. That option is available, is not available in community if you are dealing with PostgreSQL. That's a capability that we are building, but that option is available with PG Logical too, for PostgreSQL, to capture the data across multiple nodes. That's one aspect of it. And this does not need global transaction manager. Because each node resolves conflicts by itself. And they basically use some kind of telepathy to know what the other node is doing, how the other node is going to resolve that conflict. And so across the node, they basically think alike and resolve the conflict in the same way, giving you the consistent result of data. So, but back let's say about 10 years back, we had built a system, Postgres-XC, which had a global transaction manager, which was a central backbone, I would say, which did the transaction management for the whole server.
Right.
And it was a SPOF, of course. I mean, if that goes down, if that backbone goes down, the system goes down. And so we tried to give it a standby through streaming replication. I mean, a kind of streaming replication, but again, it had the same problems that a streaming replication had, that it affected HA.
Right.
So then what we have built in BDR, which is a proprietary solution to Enterprise DB, is a consensus. I mean, we have used Raft in order to maintain a global consensus.
Right.
Again, it comes with the pros and cons of Raft, but that allows to have as a distributed decision maker, I would say, distributed consensus, which can be used as a global lock manager. In fact, we have a notion of global locks in BDR. It can act for a variety of things. I'll touch base upon that aspect as well. So I think I have answered both of your questions, both aspects of the question. Anything I have missed?
Nothing per se, but I was about to ask that part. So how do you actually detect, unless you have a global logs across nodes, it's not easy for nodes to detect that there is a conflict and also resolve those conflicts, right?
Not necessarily. We don't need a central component for that. Okay, maybe the central component in those systems is time. Well, we are touching upon rather intricate parts of not just the distributed system, but the nature. So I'll leave that.
Yeah, sure.
I mean, we can talk this either offline later, if you want to delve into that.
Sure.
There are ways to do it without global lock manager using a different kind of global system, I would say.
Right.
Or some kind of telepathy.
Sure. Yeah, and the last question that I have is in the context of partitioning a table, right? If the table has multiple indexes defined, the secondary indexes kind of things defined. So as the partitions increase, wouldn't the number of indexes also increase because they are kind of different tables, right? Or am I wrong?
Yeah, in PostgreSQL, yes, partitions are different table. They will have different indexes and so on.
Right.
So there are problems that come with it, but of course you are not. And those problems are being faced. In fact, some of the problems I'm working right now deal with that kind of scalability. But the other aspect of it is we are not going to throw partitioning when the data is in MBs. You would at least need like a GB or hundreds of GB of data in order to use partitioning for scalability. You can use partitioning for other purposes, but if you want to use partitioning for scalability, then of course we need to deal with those large volumes or those large velocities. Otherwise, using partitioning is not good. Yes.
Yeah. My question was more on the scalability aspect only. Of course, this distributed concept itself would come into picture when we have that huge data, particularly. I mean, that's where it may make more sense. So now if the partitions are increasing, suppose many of the use cases could be like create partitions per month, or if you have time-based partitioning, you could say create a partition per month or something like that. So if those are the kind of scenarios, unless the partitions or the ones which are no more needed are moved to the cold storage kind of things, but otherwise as the partitions increase, the number of indexes also increase, and that introduces a lot of latency. So any distributed setup that we create based on this partitioning, wouldn't that affect scalability, was my question.
It does, but it also solves the scalability problem. I mean, of course, if somebody uses these tools inappropriately, they will face these problems. But a certain experience is required in order to use partitioning and dealing with them. But that's a larger topic. I mean, if you look at my blogs, there are quite a few blogs on partitioning, which talk about what problems partitioning solves and how to use it while solving those problems.
Okay.
I don't know if we can answer all that thing right
Okay.
now in this talk.
Sure. No, thanks for your time.
Yeah, thanks. Okay, I think I have used a lot of time, so I will go through these slides a bit faster, but please reach out to me either here or on my email, wherever, if you're interested in some of these aspects. There is a feature that is being developed for quite some time now in PostgreSQL, which is called pluggable storage. In PostgreSQL, everything is pluggable. I mean, knock and it will be open for you. That's true with PostgreSQL. You imagine that I want to do something with PostgreSQL, and you will find a way to do that even without touching the core code and in a language that you want to do. Right? So we have started developing something called pluggable storage, where the underneath storage can be changed. Now, this has potential to become a really good feature. Again, it's a pretty nascent stage right now. So you won't be able to do fancy things with it. Maybe you can replace heap with something else. There are extensions being developed to do that. But essentially, this allows a system like this, has potential to allow a system like this, where the storage is shared by multiple servers. In fact, this was, if we go back in the databases, Oracle's RAC was like the first popular, well, there are many systems that were developed before that, distributed databases, but this was most used, I would say, of course, arguably, and it was shared disk cluster. So all the things that we have talked about are shared nothing clusters. There is nothing that is shared between the servers, between the individual systems, and those are called shared nothing clusters. Most of the distributed systems that are developed today in the application world are shared nothing. So everybody takes shared nothing as a granted architecture when it comes to distributed systems. But the other thing is shared disk cluster, where the disk is shared across the nodes. Or in fact, well, there are many layers in between. You can share many aspects of that system, not just disk. So it's quite possible that a future system will plug a distributed storage under PostgreSQL. And in fact, there are systems which do that with a single server right now. that I know extensions which can deal with S3 data, and S3 is essentially distributed, I would say. But a proper system where multiple nodes will be able to talk to a distributed storage, it's quite possible using this pluggable storage. In fact, if we look at rack, the distributed storage that time was not really distributed. I mean, you could put RAID in it, but that's kind of redundant. I mean, it uses redundancy and then it's high available. But with, let's say, Aurora, probably we can put a distributed storage, which is actually distributed. But getting here, where these are also right, is something everybody is struggling with, and something which is kind of, the holy grail in these days. Everybody is trying to get there. Okay, extensions. I'll just touch upon it. It's a marvelous thing with PostgreSQL. You can imagine anything, and you will be able to do what you want through extensions. For example, we have built consensus raft, which creates a consensus layer on top of PostgreSQL servers. Through that consensus system, we have been able to do a node management across the clusters without having a global entity in between. You can then do distributed catalog management, transaction management, distributed lock if you want. All of this is possible because these extensions allow you to inject code that runs inside the server. In fact, it also allows to deal with a variety of data. Imagine whatever data that you want, the type of data, and you can add that data type in the server using these extensions. There is, there are user-defined functions allowed, user-defined data types, which can be written in C. The underlying code can be written in C, and all of that is possible. I have seen a demo where they have developed an IoT system where PostgreSQL is at the center of that system. And it does everything. I mean, there is no application layer surrounding it. Again, through extensions. So you can turn PostgreSQL into the system that you desire using these extensions. I mean, like this guy, this is no more, its shape is elephant, but it's no more an elephant, right? So that's the kind of thing that you can do with PostgreSQL. Okay, I'll touch base upon some of the things that we have been working on, then timelines, just to give aspect of what it takes to build these kind of systems. By the way, these are all the areas and many more where Enterprise DB has been contributing over all these years. All the things that we talked about, pluggable storage, logical replication, parallel queries, another aspect where you can get scaling within a single SMP box. Backup recovery, again, that's part of HA, but it helps us in building distributed system. In fact, we allow another aspect of availability is rolling upgrades and all those things, which is possible with this. Partitioning and foreign data wrappers we talked about. Okay, and so what we have been able to do in Enterprise DB through our proprietary solutions. So there is PostgreSQL community, but we have a system which can use. In fact, I wanted to have a demo of our cloud offering where you can put nodes across geographies, but I couldn't get time, and that was because distributed systems are complex. I got, over my last weekend, I got escalations which dealt with consensus, all these complex things, and I could hardly get any time to set up that demo. So blame distributed systems for any of your problems, the complexity there. So we have logical replication, we talk about, which allows us to have the data replicated across the nodes, in fact, across geographies. Data consistency, I was asked, what are the, like, if I want to have a consistent system and I'm allowed to let go of some of A and P problem, then can we do that? Yes, we have developed a feature called Camo specifically for the financial institutes, which allows consistency across these nodes. And you can control that consistency, again, at the cost of partitioning or availability, but you can control it. There are very few systems which allow you to control cap. And BDR, or now called as PGD, is one of them. Then of course, these do not come, like, these are not simple systems. You have to put a lot of tools around it so that you can get what you want from this system. And we have developed those tools. They can be deployed anywhere, in cloud, virtual, or bare metal. This is another aspect of logical replication where you can control the replication itself. You can control what data goes out of this system to other, or this geography, if we map it that way, to other geographies. Again, something possible because of logical replication, not a very not something inherent to distributed system, but something which is required by the systems today, if you want geographically distributed systems. And the next thing that we are developing, and which should be available towards the end of the year, is sharding, something called a feature which will allow you to distribute the data across the geographies, or at least across the servers. Again, as I said, with distributed systems comes complexity, and we have all the, Enterprise DB has all the expertise that is needed. It has been involved in developing those systems, supporting those systems. So you get an end-to-end solution for your database needs. I think with that, I'll stop here. If we have any questions, we can take them right now, or we can discuss it later.
Once we selected the eventual consistency, can that be converted to immediate consistency? Immediate consistency?
Yes. In distributed PostgreSQL, you can control it per transaction, whether you want that transaction to be immediately consistent or not. And there are multiple levels which you can control based on application, either at transaction level or at a particular node level. Even that can be done. Or for two particular nodes, it allows you, it gives a lot of flexibility in that area.
So you say that we can create our own data types, right? So is there any guidelines from the Postgres which we can follow before doing that?
There are examples in documentation, PostgreSQL documentation. And then there are some data types which come in the contrib modules as extensions. So you can, I think HStore is one of those examples which you can look at. And then there is, if you go to PGXN, which is basically the repository of all the extensions available on PostgreSQL, you get plenty of examples.
But before they are creating that extension, might be they have to follow some guidelines, right? Before creating that.
Yes, those you can find in the documentation as to how to create an extension, how to manage it. PostgreSQL documentation is pretty good that way, and it's all public.
And you said that sharding, we have to do a sharding in multi-regions, right? And let's say one of that sharding have some data, and due to some disaster, it will lost. Then how we will manage that sharding? Because again, we have to do the geographical sharding for that particular component, right?
Right. So with, as I showed in the slide, I can find that slide. So here, there are both things. There is a sharding interconnect and there is a replication interconnect. So depending upon the application, you may replicate that data outside that region, so that even if that region goes down, you have the data available.
For particular
somewhere else.
sharding, we have to create a replication as well.
Right. You set up both sharding as well as a logical replication. That's what we are building. Basically, a system which will allow you to do all of that automatically. It will take care of the replication as well as sharding.
Thank you.
But yeah, I mean, if you are doing it by your own, then you will need to set up the logical replica for that particular shard and be able to replicate, make the data. Okay. If there are no questions, I'll, I think, close this. Thanks a lot for coming here. And thanks to the organizers for giving me this opportunity.
Thank you for, this is great session. It's been interactive. And thanks to Ashutosh, who agreed to come down to the another end of the city on weekend. So I really appreciate, thank you so much. And I look forward, like we will invite you to more places, probably closer to your home or online, but thank you so much. So next talk is by Surut. After Postgres, one type of storage, we will move on to another type of storage files. And those are Nutanix files. I will hand it over to Surut. Please take it ahead. Thank you.
Thanks. Hello, so I'm Surut. I'm part of Nutanix files team. I work from the same office you guys are here in the Pune office. So before we talk about files, right, I want to maybe give a few minutes brief about the basic Nutanix structure or the stack, because files is kind of built on top of it. So Nutanix is hyper-converged, right? So you know about it. So essentially, when you get a node, we install Nutanix software in it. What happens is it has hypervisor, so it can create virtual machines, and it has CPU, memory, and huge amount of disks. And the Nutanix software actually gets installed into a virtual machine, which we call it as a controller VM or a CVM. So this basically controls everything. So hypervisor, you can create different virtual machines. And the storage for these VMs is coming from the Nutanix stack, which gives basically virtual disks. So this is nothing to do with the Nutanix files, but this is the core Nutanix stack on which the files is kind of built up, right? So this is one node from the Nutanix stack. It's a cluster environment. So essentially you'll have, let's say, multiple nodes, each node having a controller VM. And these VMs basically create their own cluster, right? And they're basically giving virtual disks for any user VMs which are created on these hypervisors. So I'm not sure if you guys are aware about this Nutanix stack, but this is the core of Nutanix. This is where the file begins. So this is what the files will leverage and build on top of it. So far what we have is a cluster which can give me vdisks, and since this is a cluster, I can actually it doesn't matter whether a VM is here or here, it can access all the disks in that cluster. So when we talk about files has a lot of different components. So you have protocols like NFS, SMB. It's essentially first thing you need is a file system on those disks, right? And then you have clustering, the file level, high availability will come into picture, replication, all this stack, basically we take and we install it into a virtual machine, right? Which is essentially on top of this node. So we actually create a VM here, and that's where we actually install all our files stack, right? So now the files level cluster kind of looks like this. So we have the basic Nutanix cluster, which gives me vDisks. And for like any other VM, I have a file server virtual machine where all my file stack, my protocol, file system, everything is running. And I have multiple of these VMs, essentially. And these FSVMs also create their own cluster. So all your protocol level stuff, your files level stuff is happening within FSVM. And the basic disk is coming from CVM or the core Nutanix stack. Any questions so far? Like, so this is part of the Nutanix stack, right? Without files, right? So this CVM controls all these things, which itself is a virtual machine on that system, but they have their own cluster, right? So that is core product, and files is actually leveraging it. It's built on top of that. So let me go back. So CVM, so basically it's a hyper-converged infrastructure, right? So CVM basically controls all the disk in one particular node, or actually the cluster, and it actually creates virtual disks using those things, right? So if you look at a CVM level cluster, it will basically have n nodes, and it will create n number of virtual disks or multiple virtual disks using the storage available to those n nodes. Yeah. Yeah. So we have one CVM running on kind of one node, right? Yeah. So basically, if CVM is providing a virtual disk, then there is a replication factor defined. So this CVM knows that how to replicate that data within the cluster. So there will be n copies of that data available in the cluster. So let's say if this node goes down, the remaining CVMs, they know how to construct that virtual disk using whatever data is available. That's the CVM level cluster takes care of that. Yeah. Right. And as I mentioned, the entire file stack is also now as a VM, which is available on these machines. And then they form their own clustering at file server level. So when we talk about files, it is essentially a NAS box, right? So it is giving you a NFS and SMB access or a multi-protocol access. So what happens is client will talk to any of the file servers, and file server essentially build this directory hierarchy or namespace hierarchy, which is exposed as shares, which NFS or SMB clients can access, right? So file server level, there is also, it's a clustered solution. It's a distributed system. So we talked about partitioning earlier, right? So similar stuff, what we do is we have data spread across these different file servers, and we actually refer this client to the correct file server where the data is stored. So both SMB and NFS protocols, they allow. So you can basically tell a client that go talk to this particular node for your data. And then the client will actually redirect itself to the correct FSV. Yes, so it is a highly available system. So it's a clustered system, right? So this FSVM, if it goes down, the other FSVM can serve the load. I'll talk a little bit more about it when we go. So for today's talk, right, I'm talking about 3 challenges for this file server architecture. There are, of course, 1,000 more, which we are continuing to solve, but these are kind of from one category. So basically, I think I have a good background talk here, so I'm going to build on that. So we have the same problem. Like now, we have n nodes, so n virtual disks or n into something, and I want to create a single namespace on top of that. So it's the same partitioning problem. We have a data which is partitioned across nodes, but I want to give a single namespace, right? That is one. Then how do I distribute my data so that all my nodes get utilized? So that is probably extension of the partitioning problem. So we have this distribution of data which is needed. And it is somewhere now still restricted on how much I can create a single namespace, how big my single namespace can be. So I want it to be kind of limitless theoretically, right? I want it as big as possible. So these are the problems what I would like to discuss today. Okay, so first thing what we created is a distributed share. So what distributed share does is, so for those who are not from the NAS background, share is kind of an export in NFS world and share in the Windows world. So it's how you export a file system for the client, so clients can access it. So similar to what Windows machine, you will map a drive, or NFS you'll mount. So that is basically a share. So the files is essentially giving out shares or exports, what you call it, right? So distributed share is essentially a share where we are spreading or distributing the data across the files nodes, whatever we are available to us, right? But what we do is only the top level directory kind of is distributed. So for example, if a share has 10 directories, we'll distribute few directories on node 1, few on node 2. But once a directory gets mapped to a node, everything under the directory will basically go on the same node, right? So it does solve some problems, but it is still not a best distributed solution yet. So going back to this diagram, right? So a user, so we have, let's say, 3 file servers. The data will be distributed across this file server VMs. And the top level directory can, based on some algorithm, we can choose it to go to file server 1 or 2 or 3. And based on the access, we'll basically redirect the client to that particular node. Yeah. So for NFS v4 onwards protocols and SMB protocols, they allow me a referral mechanism. So what that means is I can tell the client that your data is actually on this node. So this is that node's IP and location. So you go there and read from there. But NFS v3 does not have this ability. So for v3, what we do is we do the internal forwarding. So one node will basically talk to another node, fetch that data and give it back. So what, okay, I'll go back to this side. So we have a clustered DB layer, which is available for all this FSVM. This is our metadata layer. What we do is we maintain information about the top level directory and its location, right? So let's say user 1, we know that this belongs to on this node. Now when client, let's say, tries to talk to this node and access user 1, this server basically tells the client that it refers it to this node. It says that, okay, your data is available on this IP at this location. So that is a referral information. So that is the referral feature. Correct. So that particular metadata about the location of the top level directory is kept in a clustered database, which is available on all 3 nodes. Only for the, yes. That is also cached and all other things, right? So, but essentially that basically restricts us to keep how many directories you can basically shard. Yeah. Right. And same reference in a slightly working may be different, but the same concept works for SMB also. So SMB also you can refer saying that, okay, go to that particular. But NFS v3, we cannot do that. NFS v3 protocol does not allow that. So for that, what we do is when this request comes to here, internally, we know that the data is on this node. So we'll internally go to this node, fetch the data and return back to the client. So that is distributed share. So now we have a share which is distributed. It can use all the nodes in the cluster. It can keep its data on all the nodes. So it basically creates a single namespace. So at least one challenge is solved with this distributed share. Next is we have this connected shares actually. So connected shares is, this is done to improve the distribution. So with distributed share, if you see the distribution is happening only at the top level directories. Only I have a choice to decide whether the top level directory goes to file server 1, 2, or 3, or n. But once a directory goes to a node, anything created under that directory has to be on the same node because there's no referral available at a down level. With connected shares, what we have done is basically one share, we can connect it into the namespace of another share, right? So for example, if you see this is a one share, and this particular directory or folder, I've actually connected it to another distributed share. So anything you create under this folder, this is now as good as the top level directory from this share's context point of view. So you get all distributed nature available at a n level depth also. Correct. So without this, what will happen is you have to create a share and only the top level directories you have a choice to basically distribute the data. What is use case of? So there are applications who want to distribute at, let's say, 4th level directory, because they'll create some path. For example, home, dir1, and under dir1, they want to create n directories where actual data is created. So we want those n directories to be distributed and not the top level directory to be distributed. There are multiple use cases for this. For example, since this is a different share, we can potentially set up a different snapshot schedule for this particular subset of the namespace, or a different quota for that subset of the namespace. All these things we can achieve. So that's why this connection actually helps us. So does it make sense? Yeah. Any question on this? No, this is not a replication. So these two shares, they exist independently. Okay, but this share is also available in the namespace, in the sense, this is more like a junction created. It's more than a symlink, but logically you can think it is like that, but it is far more than that actually. But yeah, so basically whatever you create here, it will be created under this share.
How does this linkage show up?
So,
or is it just a virtual thing? It doesn't show
up. On the file system, it will not show up. Okay, but this is a separate share. So you have an option to keep it enable or disable. So that means somebody can directly come to this share and access also, or you can disable that also, right? It doesn't matter. But from the client point of view, this is a single namespace now from here onwards. So client can choose to connect here to FS1 distributed one, or there are cases where we don't want that. So this kind of hidden, and only path to this share is from this path, basically. Right. So this kind of solves the second problem, that is, I want to have a better distribution. So first problem, the distributed share actually gave me a single namespace where, see, I have this n file server nodes, right? And each of them have multiple vdisks and multiple file systems. Essentially, there is no clustered file system here. So I want to build a single namespace using multiple file systems. So that kind of is solved by the distributed share, but it actually allows me to only shard at the top level. So connected share basically allows me to shard at any depth, right? So
I think I still that confusion here. So when you created this share, it's nothing to do with which FSTM instances it's going to be. There is a virtual entity.
share,
You as a user don't really know.
Correct.
FSTM
correct,
would be hosting it, and given this example, there is no such concept probably apply, right?
correct. It is not something clients can control. It can be anywhere. Okay. So without this, what will happen is when you create this directory, so this directory is essentially getting created on one file system on one node, right? Now, how this out of this n nodes and n file systems, where it got created, that decision can be at a logically higher level. But essentially, this will be bounded to one node now, right? So anything underneath you create, it will remain on the same file system or the same node. Correct. So that means if you want to have these directories spread across the cluster for your performance or scalability, you cannot do that. So that mandates a scale up kind of an approach, because now this is on node 1. So you want node 1 to be bigger and bigger because you want to have more data underneath it. But if we can distribute this across nodes, then that actually becomes scale out architecture. Because
DLD1, DLD2 can be on two different FSTM.
Now, yes, because this is a distributed share here. So anything you create under it, it is like a top level directory. So now they can get distributed to multiple file systems across the cluster. Right?
So folder, okay, the folder 2 was created before or post fact? I mean, because if you create folder 2 on day 1, then all the subdirectories within the folder 2 go to the same node.
Correct.
So, but now that you give an example of this
So-
four directories, nodes, it means folder 2 I'm creating later on, and I'm doing sort of move, and then that's the one.
No, it's so basically what we do is folder 2 gets created. And so today we allow that. What we allow is only when it is empty, you basically say that my folder 2 connect my folder 2 and my this particular share. Okay, and we allow that connection only when this is empty. Because if it is, yeah, because if you allow existing data, then it is kind of your Linux mount on an existing directory. So original content may not get deleted, it will get hidden basically from the client point of view. So only when it is empty, that time we allow this connection. So anything after that you create inside it, it will get distributed throughout the cluster.
Size of standard one and distributed one.
Yeah.
Will show the folder 2 consumption or folder 2?
No, the folder 2 consumption is only computed by this share. But now, since this is a separate share, we have a bunch of attributes which we can set only on a share and not on a directory, right? But now, since this is a separate share, actually, you have an option. You can inherit all those attributes, all those settings, or you can actually have separate settings. For as an example, I said, you can have a different, theoretically, you can have a different snapshot schedule for this particular namespace, right? So all those things you can now do with this.
This is not a standard address, or I haven't seen such a setup before.
Okay.
Is it a standard thing even with regular NFS or?
I'm not aware actually. Yeah, but this was actually came up because our architecture, we have multiple file systems we are stitching together, right? So this was the best alternative. We did that way, right? So with this, the scale up problem is solved by the distributed share. It allows me to create a scale out kind of architecture. This enhances that even more. So now I can truly claim to be a scale out architecture. But even with this, there is one problem remains, that is my share size is actually bounded by my hardware size. And my hardware size is actually, whatever you call it, it is going to be limited. So we have customers who want kind of a very big shares, but in a traditional, like without HCI, what you have is you have separate compute, separate storage, and all those things, right? Here it is all hyper-converged. So here adding a node means adding more compute, more storage and everything. So even scale out is actually a little costly. So what we want to do is basically create a share which is kind of infinite in size, but have limited resources on-prem. So that's where the third thing what we do is we use tiering. So what we do is the cold data we move from file server to S3. And this need not be like only S3 in AWS. We support Azure or even our Nutanix object store. So we basically move a bunch of data from file server hardware to object store. And since this is tiering, this is inline in the sense your stuff file remains on the file server. It's not an archival solution. So you can still access to the files which you're moving around. So the namespace in file server remains accessible and same, but the data movement actually is done and data is now physically available with S3. So with this, even though my hardware size is limited, I can actually scale my share size to multiple petabytes. So these are the three things actually. So one is the distributed share, and then the connected shares and smart tiering, which actually increases my share size or namespace size from terabytes to higher ranges of terabytes to petabytes. So the latency will come into picture. But this is the cold data what we are moving out, in the sense the data which is not accessed for a certain amount of time. Only that data is moved out actually. So yes, if you want to still read it, the first read can be slow because we'll actually go and fetch it from S3.
Okay.
Right.
And let's say if we are fetching from the cloud storages to whatever the file system, so how much capability that file system have? So let's say S3 have lots of data, but
Correct.
how amount of data you will try to fetch from the local?
Yes. So what we do is we fetch it in kind of multiple options you have for that. So we don't necessarily bring it all back. We'll basically bring it only in cache,
Okay.
serve the particular read request and discard it. So you don't have to actually write it on the file system or the file server what you have. So you may not actually increase your on-prem footprint. The data will still remain in S3.
Okay. So how you will decide that caching mechanism? I mean, you have any rules for that to, I mean, create some sort of caching, how much data we are keeping on the system?
So, okay. So what essentially happens is even the cache for me is actually a disk. Okay. But it is not my regular disk. See, I have this, that is the beauty of the Nutanix stack,
Okay.
that I have this CVM kind of giving me vdisk whenever I want it.
Okay.
Right. So if the cache, my cache is actually on a separate file system, which is on a separate vdisk altogether.
Okay.
So it doesn't disturb my any of the core IO, and that disk size I can limit.
Okay.
Right.
Yeah.
And I can potentially add or throw whatever because it's a cache and a vdisk essentially. So that is where the core stack helps me.
Okay.
Because it helps me to get a disk whenever I want it and
Yeah.
whatever size I
If
want.
it is a total separate thing, then it will manageable.
Yeah, it's a separate thing, manageable, and then eventually you can do whatever algorithm you want, like LRU or whatever access base you want to do.
Yeah.
So there is a question on Zoom chat. The first question is, it is from RKN. If one FSVM holding the master copy, the RF1, if that FSVM goes down, and let's say you have two replicas on, let's say, two other FSVMs. Let's say you have a 10 FSVM setup, right? So there are two other replicas. So FT is 2 and then you have 3 replicas. That's 2 other replicas are on FSVM 2 and FSVM 3. Then how do you pick the replica for serving your reads?
Okay, so this is mainly a question in the CVM area, actually, not on the file server, because the replica, maintaining the replica of it is a job of the CVM. What CVM is doing is it is giving me a vdisk, and that vdisk is guaranteed to have the content, right? So let's say, and the data or the replication is actually distributed across CVM cluster, not across FSVM cluster. FSVM does not manage its own RF factor per se. It has its own replication and consistency things. But in the context of the question, that replica is managed by the CVM. So let's say this physical node goes down, right? Then the remaining CVMs know how to construct the vdisk using the data available in the cluster anywhere. It could be anywhere in the cluster, right? So these, let's say these CVMs basically construct the vdisk. And since at FSVM cluster level also there is a node down, the remaining FSVMs understand that there is a node down, and one of them picks up that, okay, I have to serve these resources. So it will pick up, it will claim for all those vdisks, and it will basically come up with two identities, one for itself and one for the node which is down.
Okay. I hope the answer is clear to RKN. The second question is, what is the file format? I think RKN, this is a regular file system. So we are not really, it doesn't really care about the underlying, it can be anything, right? It's a regular, it's like your Linux file system, your NFS.
Right.
It's very equivalent to that. So yeah, we don't really care about underlying format. Okay, I think the third question is related to that if a write operation is modifying two files, then how do you take care of atomicity? I don't think.
So yeah, that is not in the context of file server. So this is file server, right? So essentially what clients are doing is they're mounting, they're doing open, write, and close. So they have an FD.
Yeah.
So the FD, what they're writing it, right? So writing two files is actually two different contexts from the protocol point of view.
Correct.
And then protocol has all its semantics about what happens.
Similar to how NFS handles
this is NFS
UFS.
and
correct. Exactly.
So it is the protocol's mandate handle that basically.
When you recover vdisk, is file system intact or you have to create?
No, it is. So that is the job of CVM, right? When CVM gives me that vdisk, it knows where all the data is, right? So it is not giving me a fresh vdisk. It is basically giving me a view of the data, whatever I have written earlier, right? So that is it intact.
A block layer, it's completely file system.
The vdisk is consistent. So what I've written on top of that is a file system. So the file system is consistent, right? So application has written files, so application is consistent. So it is at what vertical level you're looking at the consistency. So from the CVM point of view, the vdisk is what it should be.
Works like MD, right?
Yeah, it is read-write. So, since this is a cluster, the vdisk is potentially available everywhere, right? But one of the VM basically kind of claims, it's like iSCSI reservation. So you basically claim it. So no other FSVM can access to the same vdisk at a time. And then it knows that, okay, I have these many shares or this portion of a share which I'm hosting. So it will basically claim those vdisks and create a view for that share.
Add like the vdisk concept perhaps may be alien to a lot of people.
Okay.
In a nutshell, if any of you have used a hypervisor, it's very equivalent of a data store that ESX has. So you access a vdisk like an iSCSI target or an NFS share underneath. Underlying, the data is distributed on different nodes. But as in this stack being hyper-converged, it guarantees that wherever your compute is running, your primary replica exists on that node so that your latency is very, very low. If your node which is hosting the VMs, if that node goes down, the DSF is smart enough to move the primary replica to any other node where the owner restarts, or the ownership transfers. And all of these details are explained in a lot of detail on a public website called Nutanix Bible. So the whole architecture is kind of quote unquote public. So you can read about all of these concepts and everything. And it's in a beautiful detail. So you can please feel free to go through that.
In fact, these diagrams I've used today are from Nutanix Bible. So CVM and all this architecture that probably requires more talks than files. It is far vast. But the files is built on top of it. So knowing this context actually helps. Yeah, I think That's pretty much actually I wanted to talk about it, but if there are any questions or any topic anybody wants to explore or discuss, we can continue.
Usually the problem is like large number of small files.
Yeah.
And dealing with all those inodes and everything. So do you abstract that out or is like a one-on-one mapping?
And it's a one-on-one. So if client creates a file, it's a one file for file server. Because there are a lot of constructs for a file which clients need to handle, right? Or clients and server, they both need to agree on. So for example, you're locking, there's too much stuff. So then you're talking about file server as just a data store, which is not what we have. We have actually file system and we actually create files on it.
The performance that we give is like dependent on the whatever file system plus underlying storage.
Correct.
Both combined thing will be the result performance, right?
Correct. Yes. But that is always the case, right? Whatever you do, it's your entire stack. So for us, the disk happens to come from CVM. So the disk IOs will actually impact the performance. Yeah, yeah. Correct. Yeah, you can do that. So far, we have not done. Most of our files are, there are customers who have small files, there are with big files, but so far it is generic. So we claim to be a generic file server, right? We are not catering to a specific use case. That is possible. That's a different architecture. We are not doing that right now.
Yeah, thank you for this explanation. Could you just share something on the major use cases for Nutanix files, like something you might have observed in the field or customers wise?
Yeah.
Great.
So, so this home share actually is a big use case for us. So this distributed share was actually created for home share kind of use case, where the home directories of all users of a company are saved, and then you don't mind whether each directory gets distributed and everything under that directory is on one node. You don't mind that, right? So distributed share was actually created. So internally we call it home share also sometimes. So I might have referred to that. But the home directories is a very good or prominent use case for us. Then there are, it is more like a generic, right? So we're not catering to any specific use case, but we see a lot of media use cases also. Yeah. Thanks.
Like how you provide the backup replication.
Okay.
Or even maybe high level. I think this is a good example even of archival, right? Because
yes,
if everything is cold, it's automatically on S3, so
yes,
it's archiving it, and then you are able to restore it on file basis. So if you can support, let's say, 1 billion or 100 billion files, this potentially can become a file system archival solution.
Yes, so we have been used as archival solution also, right? So people do write backup data on us. That is also one of the use cases. So from the backup point of view, right? So file server has file system inside it, which allows snapshotting. So essentially we have snapshotting mechanism, we have auto snapshotting mechanism. So you can schedule what frequency you want to take snapshot and all those things. And we have integration with multiple backup vendors who can actually read from our snapshot and save the data to somewhere else also, right? It can be another file solution or something totally different. So that is at the file server level, but there are few other technologies what we use. One is we have ways to replicate from one file server to another file server. So there are different technologies for that. Basic level, right? What even CVM cluster, it allows me to replicate a VDisk from one cluster to another, things like that, or take a snapshot of a VDisk itself. So at file server level, I can actually use this infrastructure and I can tell that, okay, take a snapshot of this N VDisk because they basically create a share for me. All right. And then that snapshot I can restore on some other Nutanix cluster and your file server comes up. So that is also a supported mechanism. So we have replication at multiple levels. We have it at cluster level, CVM level. And at file server level also we have ways. So we can actually replicate the entire snapshot of data to another file server. Or we have a smart ripple, which is basically we can choose the logical level replication, what we were discussing earlier, right? We can choose which directories we want to replicate. And then we also support N-to-1. So you can have N file servers replicating to one file server. All those things are supported at different levels. So we kind of have 3 replication technology at a cluster level and 2 at file server level.
Case, let's say a share is eventually getting mapped into multiple V disks.
Yes.
In those situations, how do you manage? Because some of those V disks could also have files which are referring to some other share.
No, so that is true. So basically what we create is we create a volume group over a number of disks. And at a volume group level, we basically manage the replication. So it's the complete set we have to do it.
So which means I think a lot of this files functionality, it piggybacks on underlying DSF techniques that Fabric has created. But are there cases where FSVM runs not on the V disks, but on standard storage resources, like let's say EBS disks? In that case,
yeah,
the onus comes on the upper layer to manage some of
right.
this
So
functionality.
that is future, which we're basically building that. So far we are not decoupled from the Nutanix stack. So far we need the CVM architecture behind. But yes, in future, most likely we'll have that. We're actually building something similar.
And
So
are there use cases where people have used this for building databases on top? I mean, like Oracle, have people run Oracle on top of FSVM?
At least in our qualification, I've seen we're doing that. Not Oracle specifically, but at least some versions of
OLTP database.
Yes, yes. But I am not aware about exactly customers, how they're using it. I may not be the correct person to comment on that. Yeah. But yeah, we call ourselves a general file server, right? So you give us any load, we claim that we support it. It's not like a specific use case file server.
So if you compare this with a standard open source like ZFS, how does it compare? Like if somebody has to make a decision, ZFS versus Nutanix files, what could be those?
So as a hobby project, you can do it in an hour, like that is not a problem. But there is a huge file stack which comes along with it. For example, your authorization, authentication itself is a big thing. Your data safety, your snapshotting mechanism, how you control. So it's the clustering solution, right? ZFS will not give you a clustering solution, right? Then the clustering solution itself is a big plus, right? You can do things at a cluster level, not at a one file system level, right? And there are a lot of stacks, for example, your NFS stack, SMB stack, all these things are combined together, right? It's a solution. It's not like only one file system you're exposing it. And these are like few things. There are, I don't know what is happening. So it's a big stack actually, which we put into there. So first of all, that's a rare situation. I don't think that has ever happened, but it's like you're taking a backup and restore it somewhere. No, that is internal structure. When a client accesses it, we have to give the client visible namespace. Internally, how we manage it, that is up to us, right? But when a client accesses it, we will know that, okay, he's accessing dir1/foo. We are going to give data for dir1/foo. Now, where we get that, that is up to us. So the backup in general is self-contained. You can actually.
Perhaps his question could be that, can I restore this onto a regular file system?
Yes.
From a backup? Maybe that.
Yes, but you will lose all the distributed stuff, and whatever we have done with the data, that you will lose basically.
Yeah, but there is no vendor lock-in.
There is no lock-in as such that once in. Yeah, yeah. So
Restarted.
His question is basically NFS v4 is a stateful protocol. So any access from NFS v4 client, the server needs to maintain some state, some handshaking for the client. So we basically maintain, each node maintains on its own. It's on the local stuff. And there is some component which we push it to the clustered stuff also. So that if this node dies and this one takes over, it at least knows which client to allow and all those things. But essentially each node is responsible in that case because it is not a clustered state. It is like the shared nothing what we talked about. In that sense, it is shared nothing. Yes. So the protocol actually does the recovery, right? So the client will send reclaims and all those things. So the protocol is capable to recover. So NFS protocol is in a way that when server restarts, server can tell client or client can detect that server has restarted. And client knows I had this N files open and I had these locks. So it can reclaim that. That is the protocol handling. We support all that basically. So a client could be connected here and let's say this node dies out. This one has taken over the responsibility. Client can continue seamlessly with this node. It will reclaim all its state. Okay, thank you. Thanks.
तो तहे दिल से आप सबका शुक्रिया. Because engineers and weekends have a different relationship. I know that very well. But that's why I really appreciate that you coming here on weekend and discussing. Nobody wants to talk about complex things, at least on weekend, right? And we are here to talk distributed systems. So you know what I mean, right? Like, I really mean that. Thank you for coming here.